Okay, thank you very much, Damian and Edgar, for the organization of this night session. So now I want to change completely the subject of the session, because you were talking about these problems, and now I'm going to talk about evolution problem, and moreover a controllability problem. So here's our problem. I'm going to consider several coupled equations, in fact systems. So I will have m equations that are coupled, and they can be either the Stokes system. This is when epsilon is equal to 0. We don't have this term, nonlinear term, or the Navier-Stokes system. So the particularity here is that we are considering that we have some coupling or order 0, and we imagine that we can act on the system by means of a control. And the interesting thing here is that we only act, in fact, on one of the equations. Okay, so our problem or our objective is the following. We want to act with this control, but remember that we have m systems, and each system is of dimension n. So what we want to do is to act with only one control. In fact, it's maybe two controls, but this control is acting only in one of the m Stokes systems, okay, or Navier-Stokes system. And moreover, you remember that in the Stokes or Navier-Stokes systems, you have n equations at each system. So here we want the control V to act in n-1 of these components of each of this system where it is acting. Okay, so what do we have before this result? So when you have, instead of these complicated systems, n-dimensional complicated systems, you have several heat equations that are coupled, but they are coupled in this particular way. So you have the first heat equation, and here you are acting with your V control, and then you don't have any other control, but you have the second equation coupled with the first equation, and then you continue like that. So in the I equation, you have a coupling with the I-1 equation. So you have, this is called a cascade system because it goes down like that. So we know in this situation that you can control, you can drive to 0 all the solutions. So you can get y1 of capital T equal to y2 of capital T equal to ym of capital T, and this can be 0. So this is called null controllability. Okay, so if I don't do nothing, if I don't have this control, the solution goes wherever it wants at time capital T. But if I act with my control, so I am putting some heat or cooling the equation, I can get the stability, I can go precisely to 0. So this is the thing we know for a cascade system of heat equations. Okay? In the Stokes situation, what we know, so in fact we are considering the two-dimensional or three-dimensional Stokes equation. We have these spaces H and V, where we have a divergence-free condition, and then the other conditions. Okay, so you have in these spaces the Stokes system. So we know that in this situation you can act with a control V and drive the solution to 0 at capital T. So that means that all the components of the system goes to 0 at capital T. In fact, what Corona and Guerrero prove is that you can drive the solution to 0, but acting in with only n-1 component, and in fact you can have this boundary, this bound for the control. So you can bound your control in the n-1 dimension by the initial data of the control with some decay that depends on the time of control. So when you are driving the solution to 0, at which time you're driving the solution to 0. So the main ideas in the proof of Corona and Guerrero are the following. So in controllability theory, it's well known that the null controllability of our direct problem is related to an observability inequality for the adjoint system. So I will have, this is the adjoint. It seems like the system we want to control, but we have two differences. So this is minus, so it's a system with this minus sign that implies that you're starting at capital T. So it's a backward equation, okay? And for this system, in control theory, we know that if we can prove an observability inequality like this one, it is possible to construct, by minimizing a functional, to construct a null control to the direct problem. So to the problem that we want to drive to 0, okay? So what Guerrero and Colón did is to prove this observability inequality. So at time equal to 0, so here we start from T, so at time equal to 0, we observe by the component, the norm of each component in our little set omega, but here we don't include one of the components. So this is the most difficult part in the proof. So what do they use? I will show you the ideas there. So they use the divergence precondition on the system in order to see that the Laplacian of the pressure that appears there is equal to 0. And then they apply to the Stokes system this operator, the gradient of the Laplacian to all the equations. And then they obtain, in fact, a heat equation on each component of the adjoint system. okay? So they look only for the first component. So imagine that n is equal to 2. So they only consider the first component of this system, and they get a heat equation, okay? So here, they can use what is called Karleman inequalities, that are some weighted inequalities, but the different thing between the literature is that in general, you know boundary conditions. But when you apply this operator to the Stokes system, you don't know what is the value of psi1 on the boundary. So in fact, you need to add some terms in the boundary. So, okay, so here is the way we construct a weight that is used in the Karleman inequalities, but I will pass very fast because we don't have time. And given this function, that in fact, what is important there is that its critical points are inside the control set and the normal derivative is negative. So you can construct another way that is related to this yellow thing, and there at time equals t and at time equals 0, it vanishes. So you can make a change of variables, integrate by parts your heat equation, and when you integrate by parts, you don't have any term in the time boundary. Okay, so it's the magic with this way. And okay, here you have some powers of L that are used for the Stokes equation. It's important for the Stokes, not for the heat equation. For the heat equation, normally L is equal to 1, and for the Stokes, L is greater than 3, but we are going to need L much more larger. Okay, so what Immanuilov, Puela, and Yamamoto proved is for the heat equation. So here I have a heat equation with right-hand side different from 0, and they are able to prove this weighted inequality. So you see this weight in front of the gradient of the function and in front of you, and they are able to bound it by a local term that is related to the control region, also with the weight. Then you have some terms that depend on the right-hand side, and you have this red term because we don't have information on the boundary. So here are terms on the boundary. Okay, so sigma is equal to partial omega times 0t. Okay, so Corona and Guerrero use this inequality on the first component of the adjoint equation, of this heat adjoint equation that I obtain applying this gradient of Laplacian, and they are able to bound not psi1, but phi1, that is the original component, and you have my local term, you have this here. Observe that with these powers, they can be absorbed for S and lambda large enough, so you can eliminate those terms. So here is not here because you can absorb with this one. And you have some local estimates on the right-hand side. And there, you use the fact that the solution of the Stokes system is divergence-free. So you modify your weights in such a way that they don't depend on the space. So this alpha start is like a minimum of the previous weight. Okay, so you bound by below. And then you see from this divergence-free condition, you can, in fact, using the first derivative of the first component, you can estimate the derivative with respect to the second variable of the second component. And all this is bounded by the weight that depends or that appears in the Kahneman inequality. And then using Poincaré inequality, you are able to bound your second component of the Stokes system. Okay, so this is all the trick. And then you have to estimate some boundary terms, and you have to work with an equation that is like that. Okay, but this can be done. Okay, so there are some other results treating coupled Stokes equations, but in general, they treat only two coupled Stokes equations, okay, or Navier-Stokes equations. So recall that we are working with M Navier or Navier-Stokes or Stokes equation, and we want only to act in the first equation. Okay, so here I write the system with this very large matrix, and it's also, I am considering also a cascade system. So under diagonal, everything is 0, and the rest can be almost everything. Here has to be different from 0 in order to obtain a cascade. So our main result is the following. So under the diagonal, every term is different from 0, and then it is possible to derive the solution to 0 acting only in one of the equations, but in fact, this can be n minus 1, okay? And we work again with the adjoint system that is not very beautiful, it's something like that. But again, you can prove an observability inequality. In our situation, the observability inequality looks like that. So you have to estimate every equation and every component of every equation at time equal to 0 from only one component. So I am putting here the first component, okay? And the first equation, but with n minus 1 here at the j component, okay? And so we need to prove again an observability inequality using the same kind of trick that Coron and Guerrero. Okay, so you need to apply this and obtain this very large observability inequality. And this can be done using again the same technique. The Laplacian of each component or each equation is 0 of the pressure. And then in our situation, we need to use a largest order operator than the case of only one equation, but you can do that. And you will have again, like heat equation. Then you can use Kahneman inequalities for this heat equation, again with no boundary data, and you solve the problem. So just to finish, I want to show you the idea in the case of the Navier-Stokes system. So the idea is the following. In an abstract setting, imagine that you want to control this system. So you are working on Hilbert spaces, you have semi-groups, and you have a B that is an unbounded application operator there. And suppose that you have an observability inequality. So the observability inequality reads like that in this abstract situation, okay? So we have some estimate on the cost of the control. So this that depends on capital T is an estimate on the cost of the control, okay? So imagine that you have this beautiful inequality. Okay, so you're going to construct some weighted Sobolev spaces, okay, with some ρ1 and ρ0 that you have to specifically construct depending on your cost of control. But this is on the paper of Liu, Takahashi, and Tuxnack. And imagine that F divided by ρ1 belongs to this space. Then, and there's a general result, you can consider this problem, okay? So the difference is that now you don't have an homogeneous problem, you have this F that appears here, okay? But you assume that this F divided by ρ1 belongs to this space. And then there is the magic that appears. Then you're able to control this equation in some sense. In fact, the thing that you can do is to see that Y divided by ρ belongs to this space, okay? And in fact, you have this bound. So the good thing is that with the weights that you construct, this ρ vanishes. So you have the particularity that ρ of capital T is equal to 0. So this inequality implies that Y of capital T is equal to 0. So what I am saying is that in fact, you may control to 0 your non-homogeneous equation with this F, okay? And then using this result of Liu, Takahashi, and Tuxnack, you're able to transform your result, your linear result, if you're able, because you're able to control my original system when I have this function F on the right-hand side, and then define F precisely as the nonlinear, so the part that belongs to Navier-Stokes. So you have to work with that. In fact, in order to have a fixed point, you cannot only work with these all nonlinearities, but you can modify your way and work in a ball. So you can work in a ball of radius r with initial datum less than r, the norm less than R, and then show that you can have like V times gradient of W is bounded by this, and to show that you have, in fact, a contraction. So if R is small enough, you can show that you have, in fact, a contraction, and then you have a fixed point. So for every linearization of your Navier-Stokes term, you can have a control because you have this result with the non-homogeneous equation. Since you have a contraction, you have a result for small data. You have a local result for the Navier-Stokes equation. So open problem, what happens if A, I, J belong to L infinity? We cannot, we are considering something that are constant. But if you have something that is in L infinity, we cannot apply this bi-gradient Laplacian and take this operator is very large. And also for people from control, what happens if we try to do a hierarchic control and with one less component, so as we do here. So, muito obrigada.